All right, welcome back. Let's continue our discussion of using a Riemann sum to estimate the area of the region bounded by a curve, two vertical lines, and the horizontal axis. Okay, so in the last video we looked at finding the lower sum approximation of the region bounded by x squared, x equals 0, x equals 3, and the horizontal axis, which is y equals 0. Now, in this video, what we're going to do is look at the upper sum approximation, and then we'll also do the midpoint approximation. So, in the previous video, we used it was the left sum was used to find the lower sum. Now, remember, left and lower do not always match, just like right hand and upper do not always match. It's a function of whether the graph is increasing or decreasing. So this is an increasing graph, well, at least over 0 to 3. Okay, so therefore when we use the right hand endpoints, it leads to an overestimate. So now we're doing the upper sum, and we're going to use the right-handed points. So, if we imagine drawing this first rectangle. Now again, we're using 6 rectangles over the domain 0 to 3, so they're each going to have a width of 1/2. That's delta x. Delta x is b minus a. Here we know that delta x is b minus a over n, where n's not a rectangle. Well, 3 minus 0 over 6, it gives us half. So each of those has a oh, sorry, you can't see that 1/2, but uh, I guess I should watch out for that picture. Delta x equals b minus a over n, which is 3 minus 0 over 6, which is 1/2. So notice that I do have it divided up into 1/2 increments here. So here's the right-hand side of the first rectangle. I go up to hit the curve, and that's my height of my first rectangle. Here's the right side of the second rectangle. Go up to hit the curve, and there's the height of that rectangle. Third rectangle, go up till I hit the curve, and there is my height. Fourth rectangle, go up till I hit the curve. There we have our height. And then this is the fifth rectangle. Go straight up till you hit the curve. That's f of 2.5, like so. And then the third rectangle, you go up. Sorry, this is not the third rectangle, the sixth rectangle, up to hit the curve. And there we are. So this is obviously an overestimate because we are above the curve on every one of these rectangles. Okay, so here we'll get an overestimate, and then in the prior example we got an underestimate, and then we'll do the midpoints and get a somewhere in between. Now do recall that our Riemann sum, the approximation is this. It's the sum from I equal 1 to n of f of c sub I times delta x. Okay, so we have our function. We have, of course, f of x equals x squared. Now, we're using right-handed points. So the way we generate right-handed points is using c sub I equals a plus delta x times I. Okay, well, notice here, okay, A is always the left-hand side of your endpoint, so the left-hand side of your region, so A is 0, B is 3, of course, N is 6, because there's 6 rectangles. We've already calculated delta x is 1/2, so we get C sub I equals A, 0, plus delta x, 1/2, times I. In other words, C sub I is just 1/2 times I. And so now we can set up our Riemann sum and say that this is the upper sum approximation is equal to the sum from I equal 1 to 6, since 6 is n, of f of c sub I. C sub I is just 1/2 times I, times delta x is 1/2. Okay, well, I guess to save myself a little bit of room here, I'm going to go ahead and just, like I did last time, let me erase this. And what is f of c sub I? That means take c sub I, 1/2 I, and plug it into the function x squared. So it's 1/2 times I squared, that's f of c sub I, times 1/2. Okay? And what can we do? Now, in the last example, I immediately factored out the 1/2. I think I'm going to hold off right now because in the, in the last example, I actually had to factor out a constant twice, I believe is what happened. And this time, let me hold off and I'll just factor out a constant in a few minutes. I get the sum from I equal 1 to 6. Let's just square 1/2 I. Of course, if you square a product of two factors, you just square each factor individually. So what's 1/2 squared? Well, that's 1/4. Then I squared, of course, is just I squared times that 1/2. Well, 1/4 times 1/2, that's 1/8. So I can factor, and it's a constant, so I can factor out 1/8 out of my sum. I get the sum from I equal 1 to 6 of just I squared. Well, that's not so bad. Let's see here. And if you want to use our identities, summation identities, well, we have 1/8, and now we just have the sum from I equal 1 to 6 of I squared. So we do, let's see, it's a fraction, it's a 6 on the bottom, and what you do is n, 6 times n plus 1, 7, times 2 times n plus 1, that's what, 13 over 6. And then let's just see what that is real fast. Of course, the 6's divide out. We have 7 times 13 divided by 8, which gives us 91 over 8. 91 over 8. And the decimal, actually not the approximation, this is the actual decimal. It's exactly equal to 11.375. I prefer the fraction version, but they're exactly equal. So that's the upper sum approximation. Now let's see what was the lower sum approximation. Lower sum approximation was 55 over 8, which was 6.875. So that's a lower sum, an underestimate, 6.875. The overestimate is 11.375. So we know that the true area is somewhere in between. Now the midpoint should get us a little closer to that. The midpoint, since here let's draw the midpoint. If you draw the graph using midpoints, what you do is you determine the height of the rectangle using the midpoint of the interval. So for instance, this will be easy to tell. The midpoint of 2.5 and 3 is 2.75. So we go straight up from 2.75, which gives us a height about right there, and that's the height of the last rectangle, the sixth rectangle. And then for this fifth rectangle, again, you go straight up. I guess that's 2.25 is the midpoint. You go straight up, and I guess you go about right there. Again, we're determining the height of the rectangle using the midpoint. Same thing, it looks like that's about the height of the midpoint. And then here, the height of the midpoint looks to be about like that. And then maybe about like right there. And it's really hard to tell right here. It's gonna be a really short rectangle. You can barely even see it. So something like right there. Okay. Oh, something like about right. Actually, that's way too high. Really short. It's gonna be really hard to tell. But there's a little bitty short rectangle right there. Now, how do you find the Riemann sum with the midpoint? Now, in general, the Riemann sum is just this. The only thing that changes now that we're doing a midpoint sum is the C sub I value. Okay, so we're still doing the sum from I equal 1 to n of f of C sub I times delta x. The only thing that's different is C sub I, the way we calculate it. Let's see. So if you want to go back up, I don't know, a page or so. Oh, there it is. Here is the C sub I we use for midpoints. And that should kind of ring a bell, because what we're doing is we're averaging two values. I minus 1 plus I over 2. So you have A plus I minus 1 plus I over 2. That's how we find the midpoints. That generates the midpoints. So A plus I minus 1 plus I times delta x. Okay. So, well, okay, the A, the B, and the N and the delta X are still the same here. Let's see, delta X, well, okay, A is still the left-hand side 0, B is still the right-hand side 3, N is still 6 because we're working with 6 rectangles, and that gives us a delta X of 3 minus 0 over 6, which again is 1/2. Each of the rectangles has a base of 1/2. Now that tells me that C sub I is going to be A, 0, plus I minus 1 plus I over 2 times delta X, which is 1/2. Okay, I can clean that up just a little bit. Let's say if we say collect like terms in the numerator, that's going to be what? 2I minus 1, 2I minus 1 over 2 times 1/2, that's over 4. Okay? So C sub I simplifies to 2I minus 1 over 4. Well, now that we have our C sub I, we can hop right in and evaluate the midpoint sum. It's going to be the sum from I equal 1 to n, oh, not I equal 1 to n, which is 6. It's f of C sub I, so that's our C sub I value, 2I minus 1 over 4 squared, times delta x, which is 1/2. I'm going to do a similar thing as the upper sum above. I'm going to do a little arithmetic before I factor out a constant. So I'm going to have the sum from I equal 1 to 6. If you square a quotient, we can square the numerator and square the denominator individually. So this is going to be 2I minus 1. Here, let's do this off to the side, actually, so we don't waste a lot of space right here. 2I minus 1. We'll square the numerator first. 2I minus 1 squared is 2I minus 1 times itself. So if we multiply the first two terms, that's 4I squared minus 2I minus 2I, that's minus 4I, plus 1. So that'll go in the numerator, 4I squared minus 4I plus 1. And on the denominator, you have, let's see, that's 4 squared, 16 times 2, you get 32 on the denominator. But, you know, dividing by 32 is the same thing as multiplying by 1 over 32. It's a constant multiple. So I can factor out a 1 over 32 and then multiply by the sum from I equal 1 to 6 of the remainder of the numerator. So 4I squared minus 4I plus 1. And now we're to the point where we can apply the sum difference property of summations. And I can take the summation of each of those terms individually. Now we gotta be careful here because that 1 over 32 out front, that applies to the entire, everything to the right. So I need to open some parentheses, and that's going to give me the sum from I equal 1 to 6 of 4I squared minus the sum from I equal 1 to 6 of 4I plus the sum from I equal 1 to 6 of 1. Okay, now I have 3 individual sums. 2 of them have a constant multiple that I can factor out. So that's going to give me 1 over 32 out front. That's going to be there for a little while. Now this first one has a 4 constant multiple. I can factor it out of the sum. So I get 4 times the sum, I equal 1 to 6 of I squared. I have a 4 here again, so that's negative 4 times the sum, I equal 1 to 6 of I. And then plus this last one, nothing necessary there, just to rewrite it. Sum from I equal 1 to 6 of 1. Okay? And now we can use our identities. The identities that are known that we've been using for several exercises now. I have a 1 out of 32 out front. So 1 over 32, open some parentheses. I have 4 times, okay, what's the sum of the I squareds? The sum of the I squareds, we do n, so it's 6 times 6 plus 1 is 7, times 2 times 6 plus 1, that's 13, over 6 minus 4. Now, for the sum of the i's, we do 6 times 6 plus 1, 7 over 2. And then for the sum of the constant 1, we just do 6, the upper bound, times 1. So plus 6 times 1. Okay? And now let's see what we get. 1 over 32. Now this is just a job for our calculator. So we have 4 times 6 times 7 times 13 divided by 6. Then we have minus 4 times 6 times 7 over 2 plus 6 divided by 32. And that simplifies, oh, I'm not sure. Well, oh well. Oh, it was 286 before I divided. So 286 divided by 32. If in simplified fraction, that gives us 143 over 16. But that is equal to 8.9375. That's not an approximation. Those are equal. Okay? I like the fraction better, but they are exactly equal. So look what we found. We found, from the previous video that the lower sum was 6.875. So let's jot that down. So 6.875, and the upper sum was 11.375. So we know that the true area is somewhere in between, and it turns out that actually the midpoint gave you it gives you a very good approximation, and the midpoint is 8.9375. So the true area is somewhere in between those two, and the midpoint is pretty close. Oh, sorry, I'm sorry, you can't see that. Midpoint is pretty close. And the midpoint sum was what? It was 8.9375. 8.9375. Okay? So, what's the actual answer? Now, we don't know how to find like the true answer. Like we are doing approximations. You're only using 6 rectangles. Now, of course, you can get a better approximation using more rectangles, and that's kind of where we're going to head next. Okay, we're at 18 minutes, so we'll put this video in the books. But in the next video, we're going to use more rectangles and then more rectangles and get the exact answer. So that's always the way to get a better approximation. So we used 6 measly rectangles. What if we use 1,000 or 10,000 or 1,000,000? Turns out like the work isn't really any extra. Like the work we've done already, whether you're using 6 rectangles or 1,000 rectangles, the work doesn't compound because we're using sigma notation. So that's the whole purpose of sigma notation, is to allow us to work quickly with these big arithmetic calculations. So we'll catch you next video where we're doing the exact same problem again, except using more rectangles to get a better and better approximation. All right, we'll catch you then.